So thank you very much for the invitation on this panel. I come from Alice and Bob. We are a company developing a qubit based on a superconducting technology called the cat qubit, hence our logo, which you don't see, which is a cat. I'm here to talk a little bit about beyond NISQ. I'm here to talk about hardware, and I mean, Peter really well introduced the problem of noise, and Alice and Bob from the beginning, we kind of said that until we tackle the error problem, it's going to be complicated to have an impactful quantum computer, and that's what we're doing. We're developing an FTQC quantum computer. So, well, the title was Promoting Innovation with Quantum and HPC Systems, and FTQC is the innovation that's happening right now in the quantum hardware system. And so what I wanted to do with this presentation is to give you an idea of what's been happening in the hardware world and why we are now moving on from NISQ towards FTQC, to give you an idea of the timeline to get prepared for those systems. What does it mean in terms of relationship between quantum computer and HPC centers? So I mean, you all know that computing power has been increasing massively, that we now have systems that are able to deal with, we're soon going to have systems able to deal with exaflops, but still, Peter really well introduced the idea that some models are getting more and more complicated, and the classical computer is not going to be able to deal with it anyway. And that's where quantum can help on certain models where multiscale multimodal systems or optimization can come in. And if we look at the classes of quantum algorithms, a lot of them are actually most useful when you have an FTQC system. FTQC, remember, is a system where you've dealt with error. You have an error correction approach. And you can see that it's quite wide. There's a number of them. The quantum advantage is going to be more or less important depending on the classes of the algorithms that you're dealing with, but still, it's a nice complement to the classical computing. Again, I mean, I suspect a lot of you guys understand that quantum is here to augment. It's here to accelerate, not meant to replace classical computers. So it's a nice tool, an additional tool in the sets of HPC Center. Now, I'm talking about, well, we've been hearing about the NISQ work that's been done. NISQ is here. You know that you have machines that have qubits, but their error rates, I don't know if we've got, no, okay. Their error rates, if you look on the left side, are quite high, 10 to the minus 2 to 10 to the minus 4. And that's why Peter was mentioning that you can only do fairly short and shallow algorithms. If we want to deal with very impactful algorithms, the kind where you're going to see a quantum advantage, you need to lower your error rates down to the 10 to the minus 7 at least, all the way to the 10 to the minus 15. Originally, NISQ, the idea was that you could improve error rates by better fabrication, better control, better isolation from the external world. However, the gains that you're getting in error corrections cannot be done passively at the level of the system or building the qubits. It needs an active step, and that's error correction. So if we summarize, we were in the NISQ era where your logical error rate was actually the physical error rate of your qubits. The challenge was that it was so noisy you had shallow depth circuits. So variational quantum algorithms are all fairly shallow. Now we're moving into FTQC. What this complicated diagram shows is that to do FTQC, what you do is you network physical qubits together so that they stabilize each other into a unit that's called the logical qubits. Obviously, you've got some physical qubits that are going to be the data, the other ones that are going to be the measuring, because we've got this challenge of quantum. If you measure, you collapse everything. So you can only do a complicated set of qubits that stabilize each other. This unit, the logical qubit, has an error rate that's much lower than the error rate of each individual physical qubit. So the idea is that you've been able to create something that is much more stable than the stability of its individual element. Now, what it requires is an additional piece of tool, actually two sets. One is your error correction code, what is the algorithm that you're going to be using in order to identify an error and to put the corrective measures. So that's a piece of software. And you need the decoder capable of measuring those signals, analyzing, sending the correcting signals for stabilizing your qubits. And now, up until now, those were theoretical. We knew that we had some codes that could be run. We didn't have the piece of equipment that could run it fast enough. And what I want to emphasize here is that last year, 2024, was the first set of publications that showed very, very fast decoders. And so Rigetti with Riverlane, Google, and last week or 2 weeks ago, IBM showed decoders that are capable of doing and processing those error correction codes fast enough so that you can stabilize those network of qubits. And that's why you've probably been hearing a lot more about FTQC quantum systems, because we now have the demonstration that we have all of the hardware tools to create fault-tolerant quantum computers. Now, I'm not saying that fault-tolerant computers are going to be here tomorrow, but it's getting there. And now we are seeing and going to be hearing much more about eFTQC, meaning early fault-tolerant computing. We know that we're going to get a logical qubit. How many logical qubits do we need in order to run any kind of impactful algorithm? Well, the hardware community agrees that it's around 100 logical qubits. In order to run the first algorithms that are about condensed matter physics, high energy physics, or quantum chemistry, you're going to need probably 100 logical qubits at least. But what we've been seeing over the past year is that everybody has updated their roadmaps, and people are putting out machines with 100 logical qubits in the next 5 years. So that's very hopeful. That's very nice. Here I'm putting the first few names, but Google, IBM, and Amazon, all of them have 100 logical qubit machines on the roadmap in the next 5 years. The reason why I wanted to give you this context is because it has a few implications in the way that you're interacting with quantum computers. What is going to change once you're going to have FTQC machines? There's hardware implications, there's changes in the workflow, and there's also ways that actually, before we get those 100 logical qubits, we can interact now. So the first observation that I want to bring is that there's a number of quantum machines that have been installed in HPC centers, and it allowed us to understand a little bit better the logistics and how to install a cryostat inside of a data center, or those kind of things. But the large majority, if you can see, 75% of them do not have the hardware, the proper hardware to run error correction codes. So there's massive upgrading to be done to those systems in order to have, remember, that piece of decoder that was demonstrated in the past 18 months. What you're going to need in order to run FTQC machines is, that's what the image on the right shows, you're going to need the error correction code and the decoder that runs into it. You need also to change a number of small components inside of your machines, such as faster readouts. Those are small electrical components. So there's an upgrade that needs to happen into the machines that were already installed. Now, the second observation I want to bring is that this is actually a table that summarizes the hardware developers, which type of qubits they're doing, when are they expecting to have those 100 logical qubit machines, and how many physical qubits need to be put together in order to have those 100 logical qubits. And an interesting point is that, so Alice and Bob, since the beginning, we wanted to optimize error correction, so we have a fairly, one of the smallest machines, but you can see that it's going to be in the thousands of physical qubits. And remember, most of the systems at the moment are dealing at the maximum in a few hundreds. And so what we're talking about is not installing a box, it's installing at least a floor inside of your HPC centers. PsiQuantum, actually, if you look on the left of the pictures, top left, they're quite fine saying our 100 logical qubit machine is going to be a building. And that's what they're building over in Australia. You can see Google system with that little person there gives you an idea of the scale. Those are massive systems. So it is not anymore about installing a box. It's about installing an infrastructure. And if you think in terms of infrastructure projects, those deadlines becomes a lot more critical. Now, workflow. Like Peter mentioned, we can only run very short systems right now, really short algorithms on NISC. So what you're doing between the classical systems and the QPUs is constantly pinging each other. So there's always, like you're sending a small piece to the NISC machine and it's coming back and then pinging, bing, and in and out. Latency becomes critical because you're constantly talking to each other. That's not going to be happening in FTQC machines. What you're going to be doing is sending a job. It's going to run for a very long time. Your classical resources you can allocate to something else, and then you come back to the classical system. So it's going to be a completely different way of interacting, and that's where your software stack is going to be changing. Now, in the meantime, while we have the hardware, I can say that you can start interacting with us. You don't need to wait for those 100 logical qubits. Why? Because we're actually using a lot of classical resources in the development of quantum computers. We still need to understand better our qubits. We need to have more complex physical models, and so that's running, obviously, on classical. We are working on compilers, and those error corrections codes that are being done, they're being done on classical systems. So we can already act with the users of supercomputers in order to accelerate quantum. We also need to optimize our algorithm circuit. So this is what a quantum algorithm circuit looks like. Each line is a qubit, and then each point lines that interconnects horizontal lines is a gate. There's a lot of optimization that can be done at the moment. What we're seeing, so I'm looking at a use case, which is the result of the publication from last month from Google. In 2023, they developed the algorithm to crack Shor, and they showed that 20 million qubits was going to be needed. 20 million physical qubits were going to be needed. Over the next 18 months, they worked only on improving the algorithm and improving their error correction codes, and they dropped it down to 1 million physical qubits. So two things. Optimization of algorithm can have a massive impact in order to say that we are going to need a quantum computer earlier. And the second thing is that FTQC might be actually useful earlier. Because if we keep on improving, we might actually need less physical qubits to run the impactful algorithms. I'm putting here a little bit our cats, because the advantage that we have on our technology by thinking in terms of error correction first is that we have the smallest machines capable of running useful algorithms. And then the final slide, I want to say that AI is actually, everybody's been talking quantum AI quantum. AI is actually super useful for quantum. We're dealing with massive amount of data on our qubits. There is a very good paper that came out last month, Quantum Computing and Artificial Intelligence. It is a white paper, actually, from a lot of quantum KOL about how AI can accelerate quantum. And it is about improving our error correction codes, improving the calibrations of our qubits, and improving the control we have over it. I highly recommend that if you're building an AI factory, or if you're building anything that's going to be running AI, you can actually use that to justify interactions with quantum, because one of the use cases of AI is actually the development of quantum machines. So anything that is about AI factories can be used to improve your relationship or increase your knowledge about quantum systems. That's it. That's me. There is a nice white paper. I didn't talk about our technology at all. That was not the point of this talk. But there is a white paper that explains what the cat qubit is and what Alison Bob is about. If you're interested in any FTQC installations, early FTQC algorithms, or how AI can accelerate quantum, I'm here for you. I'm massively overrun, so if you've got questions, I'll be here after the talks, and I'll leave John Luca to talk now. Thank you.